Okay, so today we will actually start a new lesson. No. So my exams, and that's going to be the case next time too. What exams cover in terms of the topic is what was completed 1 week before the exam, so last Wednesday. And since your Friday was essentially practice of the functions that were covered on, so everything that we did, or you did it in Lingyu in class was fine. That is basically practice for exam. So basically, first 3 lectures, we completed them all. So whatever we covered in first 3 lectures will be on the exam. This is starting lecture 4. Okay? And we kind of hinted on parts of this, but you have to go one thing by one thing, cannot learn everything at once. And we're going to talk about unavoidable errors in computing. Now, errors in computing can be any typo that you make in your program. And sometimes that typo is detected, sometimes it's not detected. If you're using existing functions, existing arrays, you could be misusing them, okay? But computer is not necessarily going to check your logic. So those are actually probably the worst kinds of mistakes where nothing is reported as error, but there is an error, okay? So those are the hard to detect, but are avoidable, right? You could have gone through it once again. You could have asked your colleague to go through it for you, and maybe somebody else. Another pair of eyes is always better to actually look for errors. So those are what we refer to as avoidable, right? And we refer to them often as bugs, though every error could be a bug. Now, there are certain unavoidable errors in computing that simply come from disconnect between what we want to do and how it's actually implemented in computers. So that's the topic here in this lecture. Okay? So again, bugs, or what we refer to as bugs, is something that is avoidable, but it's there anyway. And as humans, we're going to always do typos. Just accept it and check your code assuming that there are typos in there. Okay? And the best practice is you kind of learn how to what's called defensively program. Okay? So the best is actually not to go on for a long time before checking what you've done, or some example that you can basically calculate by hand. So the best is actually checking frequently, and as you write a small piece of code, you check it immediately, and then you move on. Okay? That way you don't pile up a lot of errors, because then it's also simply hard to have the stamina to go through a code that is like 1 page long to find all of the mistakes. Okay? So that's what I would refer to as defensive programming. Okay? Now, there are certain errors, and we're going to identify 2 of them, that you simply cannot avoid. One is truncation error. So let's say that there is a mathematical formula, a series, and by definition, this series is sum from I is equal to 1 to infinity, 1 over I. Okay? Infinity exists only as a concept. Okay? You cannot easily write it down. What number is infinity? That's the whole point. It's not a number. Okay? It's just something that is very, 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 very large and continues forever. So we cannot do that on a computer. We have to approximate it. So in that case, I'm going to, 10,000 is my favorite large number. You're going to notice that. So when I go up to a large number, I typically stop at 10,000 and maybe 100,000. Okay? So basically, I'm just going to pick a number to stop the sum and just be done. So I'm close to infinity. I'm looking at a large number of summations here, okay? But it's not infinity, simply because computers cannot do infinity. Now, and we can't do infinity all the time. I mean, infinity is a concept that you at some point accepted in mathematics. It's not something you introduce a 7-year-old to. Okay? So we also grow to accept and learn what infinity as a concept is. Okay? Well, computers they will type in INF, okay? That says that they know that, like, they're programmed to know that 1 over 0 is infinity. But that said, they don't really conceptualize infinity. So that's a truncation error. We simply had to truncate this sum to a finite number of elements. The other one is the fact that there's a finite piece of memory where I'm fitting a single number to. Therefore, if I had infinite number of after my decimal point, like pi is a famous number where they're calculating however many digits I could have after 0. I don't know what's the latest one. But I can't, even if I can calculate them in theory, I can't fit them all into memory of a computer. And that's called the round-off error. Okay? So those are the two, and that's because numbers on a computer are stored in a very specific way. Very common outcome of this is that when you are adding up a very large number and a very small number, it's at the expense of the small number. Okay? Because simply I cannot find enough space to fit both of these numbers, especially when they're number of orders of magnitude apart. And we will see why that is. Okay? All right. So before I continue talking about errors, I should also know how to measure errors. And we're going to introduce two types of errors. And you have been already exposed to it in your homework. But basically, there's an absolute error, which simply looks at the absolute difference between whatever it is that I'm trying to compute and its actual true value. So, for instance, let's say that my true length of a bridge is 100 centimeters. I measure 99. My absolute error is 1 centimeter. But let's say that, I don't know, which river is 1,000 centimeters only long, but I'm going to go with it. Okay, it's a very small river. I'll call it a brook, maybe, some sort of a stream. And I measure 99 centimeters of it. I again committed an absolute error of 1 centimeter. And we can immediately see the problem with this. 1 centimeter in the case of this bridge and 1 centimeter in the case of this river are two kind of different types of error, right? Because in one case, I missed 1/100th of a bridge, and in another case, I missed 1,000th of a river. So I'm kind of more accurate in the second case, right? So this is why we introduced relative error, where we basically divide the absolute error by the actual true value, so then we have sort of a relative error relative to the size of the object I'm trying to measure. Do we always have a true value? Do we always know what a true value is? No. The nature of the problem is that we're actually busy calculating it. We don't know what it is, right? And our numerical method might be calculating it, in which case we're going to substitute this true value with whatever is the closest approximation I have to it. That we'll see how that works, and in those cases we're talking about approximate absolute error and approximate relative error. We just work with the best data we have, essentially. So in case that I'm busy computing something, I'm going to put two latest approximations, okay, that I have in the stream of approximations that are getting better and better. And you had that example in one of your last homeworks. Remember that strange sum Sn that was sum of n minus 1 times n over 2 times x to the n minus 2. So that's a typical one, right? So the latest thing you added in a sum, and that could be actually this sum right here, if I was computing it. So I would wait for this number 1 over I to get very small, and then I would stop. Okay? And essentially this absolute error right now that I'm committing is relatively small. I'm going to stop. Okay? So we use these errors to actually stop our numerical algorithms that are computing an approximate value of something. Okay? So when this element, for instance, becomes really small, the latest one, that I'm using. That's essentially the difference between my last two approximations. When the difference is small enough, I'm going to stop. So often we design numerical algorithms so that when my error is small enough, I'm going to stop. Excellent. So let me give you an example, few more examples for this truncation error. So every time I have a mathematical formula that just keeps going, I'm going to stop at some point. That's going to be a truncation error. Okay. There's also another type of approximation, and that is for a derivative. We know when we have a derivative, okay, it's a slope, right? I'm going to briefly use the board here, so it's not going to be on the PowerPoint, but basically, if I had a function, right, my derivative at a point, let's say this point, is a slope. And the way we approximate this is to typically take two numbers, right, around this point, and take a value here and a value here, and draw a straight line. Right? And the slope of that line is my approximation to the derivative at this point. And then I let those two values shrink around that point mathematically. That's taking a limit. Right? Well, in reality, computer cannot take limit when my delta x goes to 0. It has to stop at some point. So I simply have a difference between 2 points that are very close. Okay? And that is an approximation to the derivative. In this case, we're referring to this as central difference. So this would be my xi and xi. So basically, I'm simply doing some small delta x around the value. No, this is a forward difference. Apologies, I wasn't reading correctly. Okay? So forward difference would take this as an xi. This actual point value. Okay? Again, there is certain type of truncation error because I kind of stopped at some finite difference. All right. Taylor series or series of any kind. So again, we had one example in the homework, but I'm plenty certain that you've done a lot of series. Which calculus was this? 2. There we go. So in this case, you've done a lot of these. Again, if I want to compute them on a computer, I gotta stop at some point. Now, Taylor has done an error analysis. Okay? And basically, we actually know what these terms are like, and we actually know that this, whatever is dot, dot, dot in the formula. So Taylor says, if I want to compute a value of a function at some point x, I can take a value of that function at a nearby point x0. So this is a nearby point, plus difference between the 2 points times the first derivative evaluated at that point x0, plus difference squared over 2 factorial, second order difference, the derivative, and so forth. And I can keep going. I never keep going. I stop at some point. Right? And then depending how many terms I take here, I'm going to have some approximations that are better than the others. No matter what is, if actually this series converges, then the error here that I commit by ignoring all of this dot, dot, dot part is this next order. In this case, it would be a third order derivative at some point in between x and x0 times this. Yes, evaluated for n is equal to 2 in this case. So error over here would be my R3 of x. Okay? So I know that I'm limited, and if I'm converging, I can actually see that this becomes really small. Now, computer is not going to evaluate all of these derivatives, but we're actually going to use Taylor series to actually see how our code is doing. Okay, because that's one case where you actually have we have a function that I'm trying to approximate. Typically we have it, okay? E to the x is one example. So we can actually check against a true value. In cases where I know what this Taylor series looks like, and in cases where I don't know, then I'm just going to trust the code that I checked previously. Okay. So in general, what I'm pointing out is this is how we often behave in numerical methods. I'm going to iterate. I'm going to keep going, typically in a while loop or a for loop, and keep computing some terms and adding accuracy until some error becomes small enough. So that's our stopping criterion for our for loops and while loops when we are creating certain or calculating certain value. So normally I'm going to look at some approximation xk that I'm trying to compute. If I have actual solution, then I can basically check against that. And if I don't, I just take two latest of the iterations that I computed. And when they're close enough, then I'm kind of zooming in on that value that I'm trying to compute, so I just stop. When do I decide to stop is arbitrary. And that's often built into computer solutions that are given to us. We trust them. Sometimes we can't actually detect that they're wrong, okay? But we trust them and we go with it because that's the best. That's, for instance, every value that your calculator prints out. You trust it as a true value, don't you? Yeah. Well, it has a built-in error. But it might be just fine. Okay? Let me give you an example. And this is a very crude example, but it often works. So let's say that I'm driving from Austin to San Antonio. Okay? Do I need to precisely, if I'm trying to estimate how much gas I need to have in my car, do I need to know whether I'm driving 80 miles or 81 miles? Does it effectively matter? So estimating how many miles between here and between 80 and 90 is good enough, right? So often for engineering solution, there is this good enough, okay? And most often if I give you a logarithm of something, if you know it up to 15 digits, it's good enough, which is what your calculator is returning to it. Right? So good enough is good enough. No need to, right? The fact that there are people who really amuse themselves in finding the correct digits of number pi to down however many is great. Right? But for our practical purposes, 15 or so of those is good enough. Okay? Bridges will not necessarily fall because of that. Okay? So we actually have to gauge that. As an engineer, you have to often gauge what is good enough. When you're pumping into subsurface, okay, and you're pumping fluid, we all know what viscosity is, resistance to flow. Okay? So water has a viscosity of 1 centipoise. Whether you created something that is 1.12 or 1.13 because of some additives you added to the water, it's typically not going to make or break the deal. As long as whatever fluid you're pumping in is actually stable when it gets to a high temperature, right? So the actual value, typically a certain range of viscosities that is a working range, is typically good enough. Now, in chemical engineering, we might be a little different. Okay? Typically, in a processing plant, we know down to 8 digits of what's coming in to the processing plant versus what's coming out. Because those we're designing chemical reactions. It's a chemical reactor, for instance. Okay? Those we know down, and that's where it might matter because something might explode. Okay? In subsurface, often to the accuracy that we know what is down there in the formation, certain range is good enough. So you are going to be busy gauging, given the situation, what is the accuracy that you actually need. And there is no need to spend too much time being overly accurate if that's not going to help you anyway. So again, this error is in the eye of the beholder and the person trying to solve the problem, and it depends on the problem. Okay? All right. So this delta here that is mathematically described as delta depends on you. Or if I'm giving you the problem, I typically tell you what delta to use. Okay? But again, understand that it's somewhat arbitrary. All right. So let's do a little bit of an exercise, and this is actually paper and pencil exercise. So if I know the function f, this first one, so I have a function f. So in this case, function is a given function. And I'm trying to calculate values for it close to 1. So my x0 is 1. So if f is 1 over x plus 1, what is my f of x is, so what is my f of 2? This is not a trick question. What is f of 2? 1/3. What is f of 3? 1/4. So these are my true values. Okay? Yes? Glad we agree. Now, let's say I'm trying to approximate this function, almost as if I didn't know what the function is. Okay? Except that I did. I could approximate this function by saying that f of x is f of x0, where f of x0 is 1. So what is f of 1? So that's 1/2 plus this x that I'm trying to work with, minus x0, so that's 1, times, what is derivative of f? I'm going to use f prime of x. Minus 1 over x plus 1. All of that, calculus 2, has evaporated. Yes? Do we agree? What's f double prime? 1/2 times 1 over x plus 1 to the 3, right? Okay. So write that down. Okay. So here I would actually have f prime of 1, f prime being this, plus, and then I would have x minus 1 squared over 2 f double prime of 1. And I could keep going. Now I'm wondering, depending on how many terms, this is an approximation formula, okay? You can think about it as a general numerical method, some sort of approximation. Now I'm wondering, what is my accuracy, what is my error in computing f of 2, depending on how many terms, 1, 2, or 3, these are the terms, do I keep in that formula? So let's say that I keep only one term, that's only 1/2. I'm approximating my function, 1 over x plus 1, with a constant 1/2. Obviously, I'm going to commit a lot of errors. Yes? What is the error, absolute error, if I'm computing f of 2 with that formula? So its difference, its absolute value of 1/3, which is the true value, minus approximation, which is 1/2 in this case. Yes? Okay. What is the relative error? Here's definitions of errors. So my true value is 1/3, right? Approximation is 1/2. So true value minus approximation, absolute value we have determined is already 1/6, right? Divided by true value of 1/3. So 1/2 or 50%. You typically go in percent, or you can just say 0.5. Yes? So we know how to do that now? Okay, so now take two terms and see how that improves. You can maybe put a little table. So now assume your f of x is these two things, and then all three. So calculate absolute value and relative, absolute error and relative error. And I realize now that I was writing here behind the table and nobody said anything. Is this better? Oh, look at that. Maybe this is better? I don't know. Does that work? Sort of.
Wait, is this second term negative?
Doesn't matter if it's positive or negative. It is what it is. F prime is what F prime is. Yes, it could be negative. So remember how sometimes in a series, like you could kind of go around the value until you actually converge, remember? Or you don't converge sometimes. If you're too far out from x0, you're not going to converge. Okay? So these type of series solutions, they work. Why did I move? They work only if you're close enough. Has it improved for adding second term? Yes. How much? So I got 0.25, and that's definitely closer to 0.3333, right? For using two terms? Did you get something like this? Try to get it accurate. variation of this is a guaranteed homework problem right there. We just vary functions we use. Go back to Taylor formula if that's more helpful. Let's switch back and forth. If you're done with f of 2 and f of 3, are you? We can move to solving number 2, and I would like you to do that with Python. Why not? And that's going to be also practice for our exam. First order of business is to create two functions. One will be called f, and the other one will be called df. To calculate simply those functions of x. So first order of business, two functions f and df that return value of f of x and derivative in this particular case. If you are done with the first part. And this is the solution. Sure, why not? The paper one, this is gonna be done on paper. That one you don't have to turn in, but we're gonna return this Python one. So are there questions about the first one before we move on, just in terms of mechanics? There's a little bit of calculating things accurately, right? But other than that, conceptually, we're clear on what absolute error is and what relative error is in that particular case. And this is, again, the case where I know what the true value is. Okay? That's not always the case, but in this case, we do know, so we can test against it. We're going to be able to use the true value here as well, but technically we can see what the accuracy of this formula is. And first thing that I wanted to do, I'm going to navigate to my, I wanted to do the functions. Where's my teaching? 10. So I've got a new one. So
how do I define a function? This is now, so I want to compute f of x is 1 divided by 1 plus x. Okay? So how do I define a function? What do I need to do? Yes? And I'm going to literally call it f. Why not? What do I need after this? Column. And I'm going to say fx is going to be the name I use. I'm going to compute what I need, and then I'm going to return it. Do we remember this part? Excellent. So there's name of the function is f. Okay? X is my input. Fx, I decided to call it fx, is output. So if my x0 is 1, I can simply print f of 1. It's 0.5. If I wanted to print x, what would happen? Error. Why? X is only within the function. So the moment the function is not executed, or it executed already, it was cleaned up and stayed in the function. I was in Las Vegas on Friday. What happened in Vegas stayed in Vegas. Though in my case, it's really boring. I was stuck in a meeting from 7 a.m. till 6 p.m. They served us a very nice dinner afterwards. A nice view. But other than that, it was work from 7 a.m. to 6 p.m. Anyway. And no, I didn't get crazy on the strip, but I went to see who were there on Saturday. Now that's a feat of engineering right there. Has anybody been to Hoover Dam? If you have, great. If you haven't, that's what you need to do when you go to Las Vegas. Trust me. Okay, to build that thing in 1930, even now would be a problem, but it's the best piece of concrete I've ever seen. Anyway, number of pieces of concrete interlocked. All right, back to this function. So what stays in function? So x is not known. Is fx known outside of the function? No, it's known possibly as something else if I decide to name it. So I could say, hey, my y is f of 1. And then I will know it outside of the function as y, not as fx. Okay? All right. Now, how do I actually create, another function? What's going to be my function df that creates? What should I return for my derivative? In this case, I know, so I'm programming it. Yes? If you're not sure what the order of operation is, always put extra, never hurts. Okay. Again, x and dfx are known only under those names, only within the function, and once the function is done, they're not known outside. Excellent. So what is now my approximation? I'm asking how accurate is approximation if I use, as an approximation to the derivative, I'm using f of x I plus 1. Here I'm just having two of them. So x1 minus f of x0 divided by x1 minus x0. Okay? So what is my x1? What does the problem say? It's some value close to 1, yes? I decided to check. So my finite difference, I'm going to say dfx approximate. Okay? is the difference in values of f divided, yes? That's that slope right here. It's just that it's very small. It's between 1 and 1.01, okay? Just decidedly small. In math, I would go down to the difference would go down to 0. I would take a limit. On computers, I can't do that. So it's fixed. So let's see what this is, this approximation. What would be my actual dfx? Not bad. Yes. What is the absolute error? So basically the difference between these two in absolute terms. So calculate absolute error and print it. And then calculate relative error and print it.
Are we approximating for 0.01 or 1?
So my approximation, so again, the actual function I actually have this time. So I know the derivative is this. Okay, that's my true value when I evaluate it, or I'm treating it as a true value. My approximation is this finite difference. And that's literally the slope for some small difference in this xi and xi plus 1. That's approximation. It's called a forward difference, by the way. It has an official name. So when I'm calculating derivatives, you've had differential equations, right? You can calculate derivatives when you need them using that formula. Okay? And we can solve a lot of problems by approximating my derivatives as I'm going. Okay? So I want you to submit this just by changing this to 0.1 and calculating error, and so both for 1.01 and then another one, cut, copy, paste always works, for 0.1. So I can see that I'm getting better, and it's actual error that is going to get smaller. Okay, this is closer to 0.25. And this absolute error tells me how much closer, and relative error tells me how much closer in relative terms. So I want you to submit this, just calculate what actually error and absolute error and relative error is in both of these cases. Questions? All right.
So just printing out,
Just printing out error and absolute error and relative error.
I don't get it why I got error.
Okay. What does it say?
Like division by 0.
Okay. 0.
Oh, okay.
Typo. That's called a bug. Okay, that's avoidable. All right. There you go.
for the
Did we learn
debugging.
avoidable versus unavoidable?
All right.
There you
Thank
go. Uh-huh.